Kids, time for another day of Power Series. So we're going to still talk a lot today about our geometric series. Remember the numeric one? And I used an example of our common ratio being a half. And by the Geo Series test, if your common ratio was strictly less than 1, then your series converged. And further, you could actually calculate the infinite sum, which was your first term over 1 minus that common ratio. So that's what I've done here. And then at the end of the last video, I gave you a radical idea. What if you replace the common ratio with an x? Right? It's just taking this exact same expression and hiding the 1/2 and telling you x is some number. But notice what I get out of this is an infinite, instead of an infinite series of numbers, I get an infinite polynomial, which is equal to, gasp of all gasps, a rational function. Wait, what? What? Now, it's only equal by the Geo Series test condition if your r is strictly between -1 and 1, or the absolute value of r being strictly less than 1. We call that then, since r is replaced with a number, r is replaced with a letter, I have to say anything that you put in place of r has to be between -1 and 1, and that's what this statement is. And of course, we could write it like this: an interval of which you can choose x's to put either into the infinite polynomial or to the rational function and get convergence. Now, plugging a value into an infinite polynomial and adding them all up is a little challenging, but you can plug that r into the rational function and ka-chunk, get a number, right? So for example, what if x was 2/3? 2/3 is in my interval. What is my infinite sum? 1 over 1 minus 2/3, right? Hopefully that makes sense. We call this is a power series. Further, it's a power series that was built from a geometric series. We are going to learn how to build series that are not geometric, but for now we're going to stick with our known geometric series. However, any power series of this expression, of this type, where you have, there's really an x to the 0 here, right? X to the 0, x to the first, x squared, blah, 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 with coefficients in front. That's what that C sub n is. Going to infinity. Not only is it called a power series, it's called a power series centered at 0. And I'm going to try to illustrate what I mean by centered at 0. But for now, I just want to write in your notes. I want you to write in your notes, no shift. If you have a shift, then the only difference between expression 1 and expression 2 is that inside the parentheses, before the power, there has been a shift on x. So instead of the power series being centered at 0, it's centered at a. Of course, this is a power series centered at a also. It's just that a is 0. So in other words, I could go up here and rewrite this as c sub 0 x minus the center to the 0 power plus coefficient sub 1 x minus the center to the first x minus the center squared. It's just that in this case, my center was 0, so I didn't have to write it. Here, If my center was, say, what if I told you A was 2, then you would just replace all of these A's with a 2. And what that just means is you have a shift. No shift, O shift. Still not quite clear what the concept of that shift means, but hopefully I will illustrate that for you in the next slide. So let's talk about this one in particular, where my common ratio was X. I hid it from you. I hid what the common ratio is. Here's my sigma notation, right, with the nth term in it. Here's the expanded version. One, two, three terms, and the nth term. And I claim that this infinite polynomial is exactly equal to this rational function. Condition. What's the condition? By the Geo Series test. What is the condition? This is a power geometric series. What is the condition for equality, which means convergence? That's your condition. So as long as I stay within the interval that I got from my Geo Series test, then the answer is yes. If you have a convergent series, it means that your infinite polynomial is equal to this rational function. Infinite polynomials are challenging to deal with, but rational functions, I got a lot of background in that, and so do you. So here's the picture of the function. There's the function, 1 over 1 minus x, from -1 to 1 only. You know what happens at 1, right? There's a vertical asymptote at 1. I'm only going from -1 to 1, the interval of convergence, and here is my rational function. If I only do the partial sums instead of my infinite polynomial, what if I make it finite? A finite polynomial is only approximately equal to this function. So what if I stop my infinite polynomial after the first term? We call that a constant approximation because it's 1x to the 0. And there's that graph. Look at where they meet. X equals 0. That's what I mean by the center. The center is where every partial sum meets the polynomial and then diverges from the polynomial when you move to the right and to the left of the center. So look at this constant approximator. It's a terrible approximator. It's really not approximate at all to 1 over 1 minus x. Do you see that? I mean, maybe right, maybe really, 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 really close. But what if I add another term? The linear approximation meets the function at the center, and then you can move a little bit further away from 0 on the right and left, right? Do you see that here to about here? It's not quite symmetric. The yellow line looks close enough to the black. Well, how do you think I'm going to get closer? Yep, you got it. Instead of the linear approximation, which, by the way, hello, first semester calculus, that's the linearization of that function. It's the tangent line at the center, x equals 0. We call that a first order approximation because of the power of 1. What if I want the second order approximation? I just add another term, another partial sum. It's just a longer partial sum. But notice, look at my purple quadratic. It doesn't match the function on -1 to 1, but I have widened how far I can go from 0 to be pretty darn close. How can you widen it even further? Yep. Add a finite. A finite polynomial is approximate to the rational function. How good you get on the interval means how many terms, right? None of these are infinite, but I haven't done that many. Look at that fourth degree. The fourth degree is getting pretty good. How will you be exact? How many terms do you need to match the rational function exactly on the interval -1 to 1? You need an infinite amount. So that's the idea of the center. Because there is no shift here, this infinite polynomial is centered at 0, which means think of the point of tangency between the finite polynomial and the function, and then you radiate out to the right and the left, and the more terms that you can add, the more your finite polynomial converges to 1 over 1 minus x, the function representation. Whoa. So that aside, what are just some concrete examples of what I'm going to expect you to do? So there's 2 different questions that you're going to have tonight on tonight's homework. I will ask you to find the function if I give you the series, and I might give you the series in sigma notation or expanded notation. And I expect you to give me the function. Now, the only thing I can ask of you right now is geometric. So your question is, can you find the geometric form in what I've given you? I hope so. Also, can you see that the center is 0? There's no shift on x, right? I just have x to the n or x minus 0 to the n. So I expanded it just to get an idea of what's going. Nobody asked me to expand it. I just did. Now, this is really, right, the sum of 3x to the n, right? So there's really a 1 in front of each of these. 1 r to the 0 plus 1 r to the first plus 1 r squared plus 1 r cubed plus is equal to what? Since I recognized a geometric series, a is the first term. What's the first term? What is r? The common ratio. What is your infinite sum then? A over 1 minus r. So you found the function that infinite geometric power series is equal to. Equal to. What do you have to tell me? For which values of x, though? By the Geo Series test, the condition you must meet is that your common ratio be less than 1 don't know why I wasn't put a negative there. Negative 1 to 1, therefore x must be between which of course you can write like this. Doesn't matter. That is the IOC. All the values of x, any x between negative 1/3 and 1/3, you can plug into here, and you know that the range values from this function is your infinite sum of the infinite polynomial, or the infinite geometric series when you replace x with that number, right? So any number in between here. Isn't that crazy? So that was an example of finding the function, which is the same as finding just using the formula for the infinite sum of a geometric series. This one goes backwards. So given the power, find the power series, either sigma or expanded, and the problem will ask you for it, for the given function. So given the function, find the series. So usually how a test question will be, write out the first 4 terms of. Maybe it says write out the first 3 terms and the nth term. Just follow the directions. But notice I do also ask you for the interval of convergence. So the first thing I look at is, do I recognize geo? Now, unlike the problem before, I was looking at the sigma notation to see if I recognized a geometric series. Now I need to understand that you are looking, can you match what you have to the infinite sum formula of a over 1 minus r? Sure looks like it. I think I got the power. Keep forgetting that I write it over there. Do you see that there's no shift on x? So my infinite sum, hello, is f of x, 2 over 1 minus x squared. What's your r? And what's your a? One, two, 3, 4 terms. Okay, so let's suppose they asked me, write out first 4 terms. They have to ask you for the sigma notation or the nth term. You could write it like this, or you could write it like this. This is probably how it would show up in multiple choice, by the way, right? Do you see what they did there just with the exponents? What's your interval of convergence? Now, I will have some kids that do this. Please don't do this. Or even undefined or something. Stop it, OMG. Think about what you're saying, right? No, I'm not taking the square root of all of these. Oh, both of these. Taking the square root of that does give me, right, does blow up. I just want to know if x squared is between negative 1 and 1, well, so will x be. Right, just verify that. Let's see. What if x is, I don't know, what if x is a half? Right, is a half between negative 1 and 1? Yes. Is a half squared between negative 1 and 1? Yes. Okay. There's your interval of convergence, or again, you can write it like this. Okay, so there's an example of the other way. Given the function, come up with terms in the expansion, the sigma or the nth term, only if they ask, though. Don't panic, right? Remember, the only way you know how to deal with these is if you recognize geometric. So you're like, Geo, where are you? This doesn't look, well, I mean, I have a fraction. Keep calm and do algebra. See what you want and legally make it happen. I want a over 1 minus r. See what I did there? Yeah, I got the power all right. See what I did there? Convince yourself that's still 1 plus x cubed, isn't it? What do I have now, though? I still have no shift. Nothing is happening to x before. So what is my r is x cubed? Negative x cubed. And what's my first term? The numerator, x, right? So can you write out some terms? What if I asked you to write out the first 4 terms? 1, 2, 3, 4. A r to the 0, a r to the first, a r to the second, a r cubed, dot, dot, dot. That is exactly equal to this infinite series in sigma notation. Now, here's a way that I might write. This is a little bit sloppy. You'll never see this like in multiple choice this way. Notice that I have a negative x cubed there. I could write that as negative 1 to the n times x cubed to the n, right? Do you see that? Notice that every time I have an odd power, my term here is going to be negative. And every time I have an even power, my term is going to be positive. Also, when I write it like this, I have an x to the first here and an x to the 3n here. So here's how that would really look. Where this is what I call your sign alternator. Right? That when you start n at 0, negative 1 to the 0 is positive, so I'm going to end up with a positive term. Negative 1 to the n to the first, I'm going to end up with a negative term. Negative 1 squared, I'm going to end up with a positive term because this negative is going to get squared. So I'm going to keep this positive here, yada, yada, yada. What's the interval of convergence? Negative x cubed needs to be between negative 1 and 1. Divide by a negative, flips the inequalities. Cube root. Whoops. Which really is the same as x is greater than negative 1. And x is less than positive 1 is my IOC. Again, think about what that means. This rational function looks exactly like this infinite polynomial on the interval negative 1 to 1. Everybody's exact at 0. If you take a finite polynomial, 1 minus x to the 4th, right? This is, x times 1 plus negative x cubed to the first. So if I graph 2 terms of this infinite polynomial, it will be approximately the same as x over x cubed plus 1. They will be exactly the same at 0. And then as you move to the right and left of 0, x minus x to the 4th won't be that great at approximating it, but it won't be terrible either, as long as you stay a little bit closer to 0. How can you improve? You can get more convergence series if you add more terms. Stop it here, because I certainly can't graph an infinite polynomial. All right. Last one. find the function. So your job is to find f of x represented by, and this time I gave it to you in sigma notation, and I want you to find the IOC. So I have a sign alternator. I don't really need to worry about the sign alternator in a lot of my thinking. I need to try to recognize geo. That's the only way, the only fallback I have right now. Is this geometric? It's some common ratio raised to the n. That's geometric. But notice I have a shift on x. So O shift, I have the center at 2. Right? So what does that mean? Well, firstly, when I build, right, I have to put in n, right? When I'm replacing n is 0 into both places. But you really have a 1 in front of it, right? A 1 in front of both of these. But the sign alternator just kind of gets in my way. So here's how I think of it, right? My a is 1. I hope you can see that your first term is going to be 1. Negative 1 to the 0, x minus 2 to the 0 times 1 is going to give me a 1. Here, my common ratio is everybody inside. So I could think of this as 2 minus x, couldn't I? And then what's my infinite sum? And remember, my infinite sum is going to be my function. It's the Geo series a 1 minus r. What is that? Right? I have negative x, which is positive x, 1 minus 2, which is negative 1. That's my function representation. Now, what does that mean given this whole center situation? Well, first let's go after our interval of convergence. What's the interval of convergence? Two minus x has to be between negative 1 and 1. So doing algebra, right? Negative x has to be between, subtract 2, negate, and flip it back around. There's your interval of convergence. Hey, what number is in the center between 1 and 3? Oh, snap. So what this means, if you were to put this function into your calculator, y1, but only look at a window between 1 and 3, here's what you would see. Something like that. That's what 1 over x minus 1 looks like on the interval 1 to 3. If you were to truncate this infinite polynomial after 2 terms, you would get an approximator to this yellow curve, but the center would be here. 1 over x minus 1 at 2 would be the same as this linear function, so you'd have a tangent line that kind of looked like this. If you kept 3 terms, that would be a quadratic, so your quadratic would look something like this. Notice, though, that you're all centered at 0, and you approximate that yellow curve better and better and better on the interval 1 to 3. Notice you can't use 1, you have a vertical asymptote there. Better and better and better the more terms that you add. Whoa. That's all some pretty deep stuff, and we'll do more of this in our next live session.